All right, welcome everyone. I am absolutely thrilled to have you here for this explainer. Today, we aren't just looking at rocks and sunlight, right? We're going to conduct a full-blown, high-tech planetary diagnostic scan of Earth itself. Think of our planet as this massive, intricate internal hard drive packed with ancient stored data, while its surface systems are running dynamic, real-time applications. We are going to scan exactly how the Earth concentrates, stores, and transfers energy and minerals, and how human civilization taps into these planetary vaults.
Okay, let's dive right into this. Here are the system diagnostics we're initiating today. First, we're looking at renewable versus non-renewable resources. Then, defining and extracting ore. Third, the geology of fossil fuels. Number 4, unconventional petroleum sources. 5, mechanisms of mineral deposits. And finally, we'll wrap up with the science of renewables.
Starting with Section 1, renewable versus non-renewable resources, categorizing Earth's output.
So to really understand our planet's resources, we first got to look at this massive contrast in timelines. You've got non-renewable resources, things like gold, coal, and oil. These rely on unbelievably slow geologic processes. I mean, they are completely finite within human timeframes. Basically, it's legacy energy and material left over from ancient geologic history. But on the flip side, renewable resources like solar and wind, we are harvesting those in real time. They can be replenished over a short human lifespan. So the distinction here isn't just about what the resource physically is. It's really about the speed of the planetary clock that's creating it.
Moving into Section 2, defining and extracting ore, accessing the vaults.
You know, the Earth's crust is basically packed with the entire periodic table. But finding a spot where a valuable material is highly concentrated, that is actually a pretty rare geochemical anomaly. A simple rock anomaly is just called a mineral resource, meaning, hey, it's potentially extractable. But here's the crucial point. To be officially classified scientifically and economically as an ore mineral reserve, it has to be a well-defined, proven amount of a resource that can actually be mined at a profit. So profitability and certainty, those are the strict scientific dividing lines. Okay, so once we've defined a resource, how do we actually get to it? Well, surface mining tackles these massive layered resources by just stripping away the outer non-valuable rock, which we call overburden. It operates on a staggering macro scale. Just picture Utah's Bingham Canyon mine. It is literally the largest man-made open pit on the entire planet. Huge. But if a resource is buried way too deep, or it's highly localized, or maybe the surface footprint just has to be restricted, then we switch to underground mining. Compared to an open pit, this requires microscopic precision, using these complex networks of shafts and tunnels to pinpoint those deep geological vaults. All right, Section 3, the geology of fossil fuels. Think of these as fossilized solar batteries. Because, you see, petroleum doesn't just magically appear out of nowhere. It actually comes from organic-rich, shallow marine environments. Millions of years ago, ancient microorganisms and plankton piled up in fine muds. And the crazy thing is, they had captured the sun's energy through photosynthesis back then. As those sediments lithify or turn into rock, increasing heat and pressure literally squeeze the liquid oil and natural gas right out of them. These fluids then migrate upwards through porous reservoir rocks, like sandstone, until they hit a wall. Basically, a structural geological trap, like an anticline or a fault boundary, capped by an impermeable layer of rock. That trap pulls the fluids together, holding those ancient solar batteries perfectly intact until we drill down to extract them. Now let's move to and see how this builds when we look at solid fossil fuels like coal, which actually originate from fossilized swamps. As ancient swamp material gets buried, the very first stage is peat. Then, as heat and pressure crank up, it literally squeezes the material, stripping out volatiles like water and oxygen, and steadily driving up that carbon concentration. So we step up from peat to lignite, then subbituminous into bituminous, and all the way up to anthracite, which is the highest metamorphic grade and gives us the maximum energy output. And if you added even more extreme geological heat and pressure, it turns into pure carbon, graphite. Next up, Section 4, unconventional petroleum sources, beyond the pump. So, conventional oil flows out of porous reservoirs pretty easily, but unconventional sources like tar sands and oil shale, they play by a totally different set of physical rules. For example, Alberta, Canada has these massive reserves of tar sands, which contain a highly viscous bitumen. Honestly, it's basically like a thick tar. An oil shale is this fine-grained rock holding tight oil. The huge issue here is that while these rocks have high porosity, meaning they have the space to store the fuel, they have incredibly low permeability. The fluids are trapped, they just can't flow. Because of this, you can't just pump this stuff out. It requires intensive mining, heating, and just massive energy inputs to free up those hydrocarbons. To get around that stubborn, low permeability in tight shale, a process called hydraulic fracturing, or fracking, was developed. The mechanics here are strictly based on high-pressure fluid dynamics. They pump high-pressure water mixed with sand grains and chemicals deep underground to actively create and hold those fractures open. It manually manipulates the rock's permeability, which finally releases the trapped natural gas and fluids. Now, alongside the energy we get from this, the scientific data maps out the environmental impacts too. The process is scientifically linked to potential groundwater contamination and induced seismicity, which, if you're wondering, means human-triggered earthquakes. Moving right along to Section 5, Mechanisms of Mineral Deposits. Welcome to the Planetary Forge. And this brilliantly illustrates the completely diverse ways our planet actually forges these materials. First, magmatic processes. These act like giant thermal heat maps, concentrating heavy metals like chromium as magma crystallizes. We see this in the massive layered intrusions of the Bushveld complex, or even with diamonds getting pushed up through kimberlite pipes. Then we've got hydrothermal processes. This is where superheated, reactive fluids dissolve and then precipitate minerals. It's the fluid dynamic process behind the massive Bingham Canyon porphyry copper deposit and those crazy deep ocean black smokers. Finally, we have redox reactions. These work through changes in available oxygen to precipitate elements like uranium, which you can famously find in the groundwater systems around Moab, Utah. But it's not all happening in the fiery depths, right? The Earth's surface systems are also hard at work sorting materials. Surface waters actually hydraulically sort high-density minerals into what we call placer deposits. That is exactly how you get gold panning in riverbeds. We also really have to give credit to the non-metallic building blocks. I'm talking pure limestone for our cement and gravel for our roads. And honestly, perhaps most critically, our agricultural fertilizers rely on nitrogen pulled from the atmosphere, potassium from the hydrosphere, and phosphorus mined right from the lithosphere. We've got to remember, without scanning for and extracting these exact elements, modern human civilization would literally not exist. And that brings us to Section 6, the science of renewables, harnessing real-time systems. One of the most powerful real-time systems we can harness is just moving water. Hydroelectric dams take the potential energy of gravity and water and convert it into kinetic electricity. And the macro scale of this modern infrastructure is absolutely staggering. Just look at the numbers. The Grand Coulee Dam in the US boasts an installed capacity of 6,800 megawatts. But then you look at the Three Gorges Dam in China, it operates at a whopping 22,500 megawatts. Now, while this generates massive amounts of renewable energy without burning fossil fuels, we do have to note that these giant structural alterations to our rivers impact aquatic habitats, notoriously obstructing the migration routes for fish, like salmon runs. Now, what's really fascinating here is how deeply interconnected almost all of these renewable systems are with the sun. Obviously, solar panels, photovoltaic cells directly convert the sun's constant radiation, though they're intermittent based on weather and nighttime. But wind turbines, they harvest kinetic energy from atmospheric pressure differences, which means because the sun unevenly heats the earth and creates that wind power is actually just an indirect form of solar energy. The same goes for biomass, our oldest fuel source like wood and biofuels. It simply recently stored solar energy in plants, though keep in mind burning it does release CO2 back into the atmosphere. The one major outlier here is geothermal energy. Geothermal completely bypasses the sun to tap directly into subsurface water that's been heated by the Earth's own internal magma and core. So as our planetary diagnostic scan completes, we've seen how our planet acts as this master architect. It forges and stores incredible energy in deep geological vaults over millions of years, while at the exact same time it powers massive, real-time surface systems driven by the sun. As our technology rapidly advances, how will humanity's reliance on these two very different planetary systems evolve in the next century? Are we going to keep cracking open the Earth's hard drive, or will we fully master the art of catching energy as it falls from the sky? It's a huge question to ponder. Thank you so much for exploring this with me, and keep questioning how our world works.